wrong. So, okay, here's where we left off. By the way, do y'all like the green better so far? Is it a little better? Okay, darker, good. Condensed structures. So let's recap on this. We're gonna finish talking about condensed structures, and then we're gonna get into molecular geometry and some other things today. We said condensed structures are a way to read a molecule and imagine how it is put together. So it's a shorthand notation. It's not a Lewis structure. Lewis structures show the bonds between the atoms and the lone pairs. Condensed structures just you read them and you can imagine how the atoms are connected. So it still tells you the structure of the molecule, but you have to quote imagine it. Okay. So for example, if we have ethane, C2H6, there are 2 carbons, 6 hydrogens in this molecule. That's what we call the molecular formula. We don't know how the atoms are connected though, but if we read the condensed structure, CH3, we see the same number of carbons, same number of hydrogens, but we can read it in groups, okay? Remember, you have a main chain, or what I call kind of a central main chain atom. Those are usually carbon. What all can be a main chain? Let's define that really quick. I don't want this to be confusing to anyone. The main chain atoms could be a carbon, it could be a nitrogen, an oxygen, you could have a sulfur, you could have a phosphorus. There are probably other atoms, anything that can have more than one bond on it, okay? Could be main chain, could be. Sometimes you will see oxygens on the perimeter as a branched off of the main chain, but there's a specific way you'll see that. What cannot be main chain? Okay, what cannot be main chain are atoms that can only have one bond. So hydrogen and any of the halogens. Fluorine, chlorine, bromine, iodine. These will always be branched off of the main chain, never in the main chain, all right? So keep that in mind, because as we read these in groups, we see that certain elements are branched off of what we call the central main chain. So I started to draw, I believe, I can't remember how far I got with this class. I started to draw out this molecule down here just to so that you read it in groups. So you're going to find your main chain atom, and then what's grouped with it is everything that would be bonded to it. Sorry, I need to turn my phone on silent. So for example, you would read this in groups. Here's carbon is our main chain atom, and then the elements that follow until you get to your next main chain atom, those are a group. So here's group number 1, CH3. So I would draw a CH3 group. And I like to draw these out from left to right. So I'm going to start on the left, draw my carbon and 3 hydrogens, and then I'm going to expand the molecule towards the right. And then what is this carbon? This first carbon is connected to the next main chain atom, which again here is a carbon. And so then this is a group, CH2. And so there's our CH2 group. Okay, 1 hydrogen up, 1 hydrogen down. So you read these in groups like this. And then we'll get to talking about parentheses in just a second, because I'm going to show you. So I'm not going to draw out this whole molecule, but you could continue it just as we're doing. And you would see the whole Lewis structure for this big, long molecule. Okay, now if you're looking at these structures down here, we're probably not going to draw out every single one of these today for time's sake, but we'll do a couple different ones. You see some parentheses thrown in. And so what do parentheses mean? They are also used to further abbreviate condensed structures. So parentheses are used in different ways. Let me show you 2 examples. Let's look at A right here. We have CH3, and then we have a parentheses with a CH2 group in it, and then we have a little subscript of a 3 right there outside the parentheses. What does that mean? So this is one way to use parentheses. All that means is that we have 3 CH2 groups connected, bam, 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 in a row. So what does that look like? Let's draw the structure first. I'll put my CH3 group. Have a pencil and paper. Be drawing these with me. Try to draw them ahead of me, in fact. Now we're going to expand what's in the parentheses. We have 3, that's what the subscript means, of everything that's in the parentheses. So that means we have CH2 groups. There's 1. Here's another. I haven't connected the main chain yet. Here's another. So there's my 3 CH2 groups. I'm just expanding them left to right. And then we would just connect all those groups. Now, what concludes the molecule, this last group on the far right, is another CH3. Remember, hydrogens are always going to be branched off the main chain. So that's what this molecule would look like. So that's one example. Is sometimes if you have a lot of the same group, so we had a lot of CH2 groups, we had 3 of them right here. If you have a lot of the same thing, you can just squeeze it all into a parentheses and write how many of those identical groups you have. But they have to be in a row, okay? If they weren't all connected, we couldn't do that. Like if there was something in between this, like an oxygen or something, we could not use that style of parentheses, okay? Let me show you another example though, another way we use parentheses in these structures. If you look down here, I'm gonna do number E. Number E, y'all hear me? We have some oxygens in parentheses, okay? And so what does this mean when we have, and there's no subscript outside of it. So this is a different way to use parentheses that tells us what is branched off of the main chain, okay? When you have an atom like oxygen or nitrogen in parentheses, or sulfur even, when you find it in parentheses and there's no subscript, it just means that it's branched off of the main chain atom that comes directly before it. So let's start drawing this. I'm gonna try to draw it pretty small. We're gonna start with this first group, this CH3 group right here. Okay. And then what do we have next? This main chain carbon is connected to our carbon number 2. So there's our second carbon. Now we have an oxygen in parentheses. What that means is that, I'm going to erase a little bit so I can draw this. This is branched off of that preceding main chain. Now, what do you know about oxygens? When we talked about Lewis structures last Thursday, they have to have how many bonds and how many lone pairs to satisfy the octet? They have 6 valence. They want 2 more. Every time you share an electron to form a bond, you gain 1. So they're going to form 2 bonds. They're going to share 2 unpaired electrons, and they're going to end up with 2 lone pairs. So this oxygen, and here's the deal. Over here on my carbon, you can branch it up or down. It does not matter. I'm going to branch it up. It's got to have 2 bonds, and it's only connected to carbon, so I'm going to put both of those bonds on carbon. There's no other element that is bonded to this oxygen. Draw my oxygen, and then I'm going to put 2 lone pairs. Remember, a pair is 2 electrons. 2 single electrons in a pair. We have 2 pairs, so that's 4 electrons total. Okay, so now that's the second group. Now let's keep going. This carbon is connected to the third carbon. So this is carbon number 1. Here's carbon number 2. Here's main chain carbon number 3. And don't get it in your head that carbon's the only thing in a main chain. It's just we see a lot of that. So I'm going to draw my third carbon here. And then what do I see is connected to that carbon and branched off of it is 2 hydrogens. Okay? And then guess what? Carbon number 3 is connected to carbon number 4. We have another CH2 group. So I'm going to draw another one of those. And then again, we have a carbon with an oxygen in parentheses. So that's going to look exactly like what we drew just a second ago. A carbon with an oxygen in parentheses, and that oxygen has 2 bonds, 2 lone pairs to be satisfied. Now, here's something new. We have an oxygen right here in our structure, but it's not in parentheses. So what does that mean? Well, we said earlier, oxygen can be part of the main chain. And when you have an oxygen or any of these atoms right here that I'm underlining, any of these, when they're not in parentheses, they're part of the main chain. So what that looks like is I'm just going to draw an oxygen, connect that carbon. And then on the other side of this oxygen, because we know oxygen has to have 2 bonds, it's bonded to a CH3 group. And we know oxygen has 2 bonds, and there's its 2 lone pairs. Now, again, you always want to double check. Here's some questions you need to ask. Does every carbon have 4 bonds? Does every hydrogen just have 1 bond only? Does every oxygen have 2 bonds, 2 lone pairs? If you had halogens in your structure, does it match how it's supposed to look? I guarantee you on the exam, some people are going to draw me a structure that looks like this. I mean, I will get all kinds of ridiculous stuff, okay? And then we'll have carbons with 5 bonds on them. We'll have carbons with lone pairs. We'll have hydrogens with more than 1 bond. Don't do that. Make sure you know the rules for how each element should look to help guide you as you draw these structures. Now, which one of these, B, C, D, or F, looks the hardest to y'all? We're going to vote. Which one do you want to do? I'm going to draw one out, and then we're going to move on. F. Okay, I've got multiple Fs. I knew y'all would say that. What in the world does this guy look like? Well, remember up here when we talked about the parentheses and the subscript, it just means you have two of these identical groups branched off of. Now here's the confusing part about F. What is it branched off of? We always said these are connected to the thing preceding. Well, we don't have anything preceding these large groups in parentheses. So it means that they come first, okay? And it means that both of these groups are branched off of that carbon. That's the only thing they can be branched off of, okay? So here's how this would look. We have a CH3 group, a CH2 group, and an oxygen. And this oxygen is actually going to be the thing bonded to the carbon, okay? And then lastly, this carbon is also bonded to that oxygen. So that's kind of how it should look. Let's start drawing that. I'm going to draw one of these groups in parentheses really quick. Okay, so I drew my CH3 right here. So that's, I'm going to call it carbon number one. And then this is going to be, we're getting a little cluttered in here. This was carbon number one, carbon number two. And then we have an oxygen. And we said this oxygen is bonded to this carbon. So I'm going to bond it to a carbon. So this is one, and we're going to put 2 lone pairs. This is one of the groups in parentheses. Now we have another identical group, also bonded to, guess what? This carbon. And how I'm going to draw it, I'm going to draw it as best I can. I'm going to start down here and draw it upwards. You can do this however it will fit on your paper, is the easiest answer. So do you see what I've drawn? I drew my CH3 group. Okay, that's this group right here. So again, this would be carbon number one, and this is the second carbon. This is my CH2 group that we had. And then I have an oxygen with 2 bonds, 2 lone pairs. That's this oxygen, because we have 2 of these groups. And that's connected to this carbon as well. So what we've done, I'm going to go back to my pink. We have 2, oh Lord. We have 2, I need my pencil. We have 2 identical groups. I'm going to circle them real quick. These are the 2 identical groups, okay? That is what's in parentheses right here. And there's 2 of them. You can see that they're identical. Now, how do we finish the molecule? We have an oxygen bonded to this carbon. And it's got to have 2 bonds and 2 lone pairs. It's the only thing. And so looking at this, that's how this molecule looks. It looks very bizarre. But if you learn how to read these, you can totally draw this. And now we need to make sure, do all of our carbons have 4 bonds? What about this carbon right here? Does that carbon have 4 bonds? It's got 2 single bonds. Here's 1, here's 2, and then it has 2 more, a double bond. So 2 single plus a double bond, that's 4 bonds. And our other carbons also have that. Every oxygen, 2 bonds, 2 lone pairs. Every hydrogen, 1 single bond. So that satisfies all of our rules. So yeah, I agree. F was probably the trickiest, and but that's how you would draw it out. Now, here's also what I want you to think about. You're going to have you're going to have something that looks like this, but it'll be at the terminal end of the molecule. It won't be the first thing, it'll be the last thing. You'll have something that looks like that on the lab. A CH3 in parentheses with 3 around it. And it will be branched off the carbon for it. On the lab, there's a molecule. This right here that I just circled is at the end of the molecule. So think about how that would look. You're going to have this carbon, which is actually this second carbon right here, with 3 CH3 groups. Okay, now I haven't drawn all the bonds to the hydrogens out, but that's what this should look like. And you would then expand each of those CH3 groups and show me all the bonds with the carbons to the hydrogens. Okay, so there would be literally 9 bonds there that we're not seeing, but that we should see when you draw the molecule out. Whoops, where am I going? Okay, so that's condensed structures. How to read them, how to write them. You'll have these structures on the exam. The only way I can do these is a file response question, unless I get creative with a multiple choice. Okay, if you have questions on those, shoot me an email, set up a Zoom with me. We can work some more. I'll put some problems on our textbook back of the chapter list that I'll post soon. You can work more practice problems of these, but other than that, we're going to move on. I encourage you to practice B, C, and D on your own. Okay, let's talk about molecular geometry. We are now going to understand, you need to understand that molecules aren't just two-dimensional, okay? Condensed structures and Lewis structures, they help us visualize how atoms are connected, but they only help us visualize that in 2 dimensions. Molecules are 3D. We are 3D, and we're made of molecules. So we need to understand how they're arranged in a 3-dimensional perspective. So that's what this is all about, molecular geometry. So Lewis structures, I'm just reading the slide here, they help us keep track of valence electrons and geometry, or the shape of the molecule. And as usual, electrons are behind everything here, right? Electrons are always responsible for everything. So electron location determines the shape of the geometry, all right? So let's look at these pictures that I have. This is a figure from your textbook. We have these are actually different space filling models. And maybe in high school you've done there's kits you can buy. Teachers can buy kits, and there's all these spheres and these little rubber pieces that connect them. Maybe you've done one in high school before in a science class. They're very common, but you can see that there's different shapes based on how many atoms are bonded to what we call the central atom. I'm going to say that again. You can see there's different shapes based on how many atoms are bonded to the central atom. Okay, right here we have 4 bonded atoms, 4 white spheres. They all represent the same kind of atom bonded to this central atom, which is the carbon. Okay, so that's the carbon, and the white is the hydrogen. This is a molecule of methane, CH4. And they're spaced out as far as they can get from each other in a 3-dimensional kind of way. Ammonia, NH3. We see 3 hydrogens. They're all spaced out as far as they can be. But what do you know about nitrogen? In a Lewis structure, nitrogen has 3 bonds and a what? Three bonds and a lone pair. And a lone pair. So we don't see that here. Okay, so let's talk about what's visible and invisible on these structures. What's visible is we can see the atoms and we can see the bonds. What do we not see? We're not seeing the lone pairs. Okay, it's way more difficult to visualize, actually see electrons than it is to see atoms and bonds. So keep that in mind when you're drawing geometries on the actual molecule. The lone pairs do matter for how you determine the geometry. They absolutely matter, but you don't really see them when it comes to drawing the shape and the geometry of the molecule. Okay, you just draw the bonds and the atoms, but you consider the lone pairs to actually get the correct naming of the geometry. So for example, if we drew the lone pair in on this nitrogen, and I'm going to put a little bubble around it, you can see that there would be a lone pair sticking straight up on that nitrogen. And lone pairs are kind of the, what's the best word? They require the most space. They're kind of bossy. They tell the other atoms where to go and how close to be, or how far apart they can be. They limit how far apart other atoms can be when they're bonded. What do you know about oxygen in water? We have 2 bonded hydrogens. Oxygen has 2 bonds and 2 lone pairs. So this oxygen would actually have some Mickey Mouse ears. Speaking of ears, I bought my daughter a Halloween costume at Walmart. Elsa. She's going to be Elsa. She loves Frozen, okay? But I brought it home. I was so excited to show her. I said, Finn, her name's Finn. I said, Finn, do you want to be Elsa for Halloween? And I showed her the dress, and she goes, no. And I was like, well, fail. But our newborn's going to be Olaf, and I told my husband he has to wear those headband reindeer ears to be Sven. If you've never seen Frozen, you need to go watch it. So there's that. All right, what do you know about HCl? Chlorine here has 3 lone pairs that we're actually not visualizing. So I'm just trying to make the point here that we don't see the lone pairs when we actually have the correct geometry, but we consider them when we name it. All right, now all of this falls under what we call the Vesper model. What the heck does Vesper mean? It is valence, shell, electron, pair, repulsion. V-S-E-P-R, Vesper. So what that means is that the electron repulsion between lone pairs, that's what's driving the shape of the molecule. That's why we name it this kind of model. Okay, valence shell, electron pair, repulsion. All right, so what's happening is that electrons in the bonded atoms and in the bonds and the lone pairs, they repel each other. Remember, bonds are made up of electrons. A bond is 2 electrons. They repel each other because they're all negatively charged, and negative charges repel. And so they try to get as far apart as possible because of that repulsion, and that's what forces the geometry. That's what determines the shape. Okay. So now we're going to look at 3 rules for how to name things. So we had 5 rules for Lewis structure. We've got 3 rules for how to name geometries. What are these rules? Well, first you draw the Lewis structure. And then you're going to find the atom whose geometry you're interested in. This is not every atom in the molecule. This is usually just the central atom. And notice I put an S here because you can have molecules with multiple central atoms. But this brings up a really good point. You're never going to name the geometry of a perimeter atom or a non-central atom, okay, like a hydrogen. We'll never name the geometry of a hydrogen. Then you're going to find the number of, these are called charge. I'm going to introduce something new here, charge clouds. All right. So we're going to talk about what a charge cloud is. So you're going to find the number of charge clouds on the central atom. You're just counting the charge clouds on the central atom. Okay, what is a charge cloud? These 2 bullet points underneath tell us bonds are charge clouds. And that includes double and triple bonds. Double, triple, and single bonds, they all only count as 1 charge cloud each. That's kind of confusing because a triple bond has 3 bonds. People would be tempted to count it as 3 charge clouds, but that's not the case. A triple bond counts as a single charge cloud the same way a single bond is a single charge cloud, okay? And then lone pairs. Each count as 1 charge cloud. I actually think this stuff is kind of fun because it's like a puzzle. I'm going to show you how it's like a puzzle. And then lastly, you're going to predict the shape, okay? So charge clouds will move as far apart as possible, bonds and lone pairs, and it requires you to visualize the molecule in 3D. That's the whole point of this, all right? This right here is the whole point of what I want you to do. I want you to visualize the molecule in 3D. So this table that I'm showing you now is in your textbook. But I have a bone to pick with this table. I'm going to edit it. Instead of this saying number of bonds, I wish this said number of bonded atoms. And I'll show you why in just a minute. Number of bonded atoms, okay? So that's the header for this first column. So how do we read this table? Well, you're considering the central atom, right? You're going to look at how many atoms are bonded to my central atom. So for example, if we have a molecule that looks like this one over here that I'm boxing in, our central atom is the sphere in gray, and we see 2 branched red spheres. So that means we have 2 bonded atoms here. How many? Then you're going to ask the question, well, how many lone pairs? Because a lone pair can be a charge cloud too. And the whole point is we're trying to count up charge clouds. If we have 0 lone pairs, then you would see we have a 0 here. So total, you add these first 2 columns up, and that gives you the total number of charge clouds. So 2 plus 0, we have 2 charge clouds. So how do we name something that has only 2 charge clouds? We call that linear. That molecule will always be a linear molecule, and you know what linear means. It's kind of a flat line. A great example is CO2. Now you may be thinking, but I do know that there's lone pairs in this molecule, and you're absolutely right. We got lone pairs all over these oxygens, but they are not on the central atom. So we don't consider lone pairs on non-central atoms. We're just trying to name the geometry for this carbon here. Carbon is the central atom. Oxygen can at times be central atoms, but it's not here. All right, questions on molecules that are linear. All right, so you can see so on and so forth as the number of bonded atoms increases, or as the number of lone pairs increases and you get more charge clouds. In fact, for having 3 charge clouds, there's 2 ways we could add that up. You could have 3 bonded atoms and no lone pairs. That will give you 3 charge clouds. What does a molecule like that look like? We call it, I'm going to tell you how to pronounce this. I wish I could hear you guys attempt it in your head right now. I get all kinds of things. Trigonal, it's trigonal planar. Everybody say it with me. Trigonal, say it out loud where you are right now. Trigonal planar, okay? Trigonal planar. We could also have 2 bonded atoms, 1 lone pair. That will give you 3 charge clouds. What do we call a molecule like that? We call it bent, okay? Now you can see the difference, okay? These 3 red spheres up here, they are equally spaced out around our central atom, all in the same plane, all right? And then the molecule that we're calling bent here has 2 bonded atoms and a lone pair that are spaced out around the central atom, same plane, but it's just that we have 2 atoms and a lone pair. The top one is just 3 atoms. So, and then this last column just gives you examples, okay? If we had a carbon that is trigonal planar, here's an example. We have 2 bonded hydrogens and an oxygen. Now, what are these wedges and dashes showing you? This hydrogen is, it's pointing backwards, okay? So this is in a backwards plane. I'm going to say back plane. And this one is a forward plane, okay? It's like that hydrogen will be coming out of the screen towards us. And then this carbon and oxygen would be in the same plane, all right? So that's what the wedges and the dashes indicate. Trying to indicate 3 dimensions on a 2-dimensional screen. All right, bent, you can just see the example there is SO2, sulfur with 2 oxygens and a lone pair on it. All right, let's talk about when we have 4 charge clouds. There's 3 different ways things can add up to give you 4 charge clouds. First way would be that you have 4 bonded atoms on your central atom. If that's the case, then you don't have any room for lone pairs. This is commonly what we see with carbon, right? Because carbon always has to have 4 bonds, and no, it can never have lone pairs. So carbon, like almost all the time, I say almost because it can be trigonal planar if it has a double bond, but carbon is like 90% of the time tetrahedral. All right, so the example here, guess what? Carbon with 4 hydrogens, a molecule of methane, CH4, we call that tetrahedral. If you have 3 bonded atoms, 1 lone pair, NH3 is usually the example molecule here, and we call this pyramidal. Pyramidal, okay? We got trigonal planar, tetrahedral, pyramidal, bent, and then another way though, there's 2 ways something can be bent, even though the numbers are a little different. If you have 2 bonded atoms, 2 lone pairs, so that's a water molecule. That molecule is bent the same way that SO2 up here was bent. Because remember, when we draw these out, we actually don't see the lone pair. So the fact that there's 1 lone pair up here on SO2 and there's 2 lone pairs down here on H2O, that doesn't matter because when we draw the molecule, we don't draw in the lone pairs. But we use the lone pairs to name the geometry. Okay, so we're going to talk about this a little bit more in the coming slides. In fact, I've actually gone into it pretty in depth with this table. But remember, you're just adding up, oops, pencil. You're adding up the first 2 columns to count the number of charge clouds, okay? So just to recap here, something that is linear, you will need to memorize these. You'll have access to this table on exam 2 because you're allowed to use your notes. But this will go way faster for you, and it will take you less time on the exam, and you can spend more time on other things if you memorize it. Also, another thing on exam 1, sometimes people uploaded pictures where they had literally written down word for word the question. And that really confused me. Why are you taking all this time to, these were lengthy questions in some cases. Why are you taking all this time to write down the question instead of just working the problem? You should be able to see the question on the screen. So why do you need to write it down? So if you're one of those people who are writing down the questions, I would love to know why. Don't waste your time writing down the question. You can see it. Just work the problem. That's going to give you more time. Okay, anyways, I'm done preaching. 2 bonds, 0 lone pairs linear. The example, two examples here. CO2 was the one we looked at on the table. And remember, there are lone pairs on the oxygen, but we're just considering, for charge cloud purposes, only lone pairs that are on the central atom. Another great example is HCN. Okay, we have these 2 branched atoms off carbon. How do we count the lone pairs here? How do we count charge clouds? That's what I mean. Okay, well, we have a single bond, and this is one charge. I'm going to abbreviate charge cloud. This is 1 charge cloud. We have another triple bond, but remember, that is just 1 charge cloud. And we have no lone pairs. So 2 charge clouds is always linear, right? Again, we have double bonds right here between the carbon and the oxygen, but this is just 1 charge cloud. A double bond and a triple bond and a single bond, they're always just 1 charge cloud. So that adds up to 2 charge clouds, right? That's the slide. Those molecules are always linear. Okay, let's look at the next one. We said 3 bonded atoms, no lone pairs. This was trigonal planar. It shows you 2 views, a top view and a side view of the same molecule. So this first one is if you're standing over it looking down. And you can see that these atoms, the hydrogens and the oxygens, and they haven't drawn the lone pairs in, but this oxygen would obviously have lone pairs, they're roughly 120 degrees. They're equally spaced around this carbon, okay? So roughly, we say approximately 120 degrees. It may not be exact. You can see sometimes it's give or take a few degrees, but they're equally spaced, okay? Why is that? Well, again, because the bonds have electrons in them, and electrons repel one another, and the farthest apart they can be is 120 degrees away from each other. All right, so that's what this little text over here is explaining to you. Remember the dashes and the wedges. This hydrogen would be backward, pointing back, and this one would be coming forward. You're not going to have to draw dashes and wedges for the exam, but I want you to understand that kind of notation. Okay, we're still on 3 charge clouds, but there was another way you could have 3 charge clouds instead of just 3 bonded atoms. And hey, I'm saying 3 bonded atoms. Remember, that's what I prefer it to say. I'm just not writing it in on every slide. So wherever it says bonds, I like to say bonded atoms. That helps technically me actually count charge clouds better. Okay, 2 bonds, 1 lone pair. That adds up to 3 charge clouds, and we call this bent. Okay. So again, here is the view of the molecule minus the lone pairs. But absolutely the lone pairs count when we are determining the geometry. Okay. So again, you have a top view of this molecule and a side view of the same thing with the dashes and the wedges. And again, lone pairs on the branched atoms here, but they do not count. You're only counting lone pairs on the central atom. That's the one you're naming the geometry for. And again, these are spaced roughly 120 degrees apart. I'm not going to make you report degrees, okay? I'm not going to say how many degrees would 2 atoms on a trigonal planar molecule be spaced. That's not going to be a question on the exam. So don't worry about messing around with memorizing degrees, how far apart bonded atoms are. I just want you to be able to look at something, count charge clouds, and name the geometry, okay? 4 bonds, 0 lone pairs. This was tetrahedral. Why do we call it tetrahedral? Well, if anybody's had geometry, when you have a shape with 4 sides, you call it a tetrahedron. And these top pictures up here are just kind of showing you different models of that. It's trying to show you the different, if we made this CH4 molecule into a geometrical figure, it's trying to show you the faces of the shape, with carbon being your central atom. How far apart can the bonded atoms be for a tetrahedron? only about 109.5 degrees apart. So these bonded atoms are forced closer together. Why? Because there's one more. We only have 3 bonded atoms on trigonal planar, or even 2, and a lone pair on bent. But here we have 4 bonded things, so they're a little more smushed together. 109.5 degrees is as far apart as they can get. And again, the classic example here is this CH4 molecule, with carbon being your black sphere and the hydrogens being your white spheres. Questions there? Another way we can have, remember there's 3 ways to get 4 charge clouds. Here are 3 bonded atoms, 1 lone pair. We call this pyramidal. The example molecule is always NH3 because you have these 3 bonded hydrogens, 1, 2, 3, and you have your lone pair. Okay, now what's the degree of space between these 3 bonded atoms? It's 107. Why is it slightly smaller? We have 4 things coming off of the central atom here, just like we did in the previous slide. Up here, we had 4 hydrogens coming off the carbon, but the bond angle is 109.5. Why are these hydrogens smushed even closer together? It's not by very much, only like 1.5 degrees closer. But why isn't it the same? That's because electrons are very bossy, okay? They take up more space than anybody else. So they force those bonded atoms even closer together. Man, I promise I don't have COVID. Just a tickle in my throat. All right, 2 bonded atoms, 2 lone pairs. This is also 4 charge clouds, and this is bent. So there's 2 ways things can add up to be bent. Both have a commonality, 2 bonded atoms. The difference is the number of lone pairs in each case. 2 bonded atoms and 1 lone pair is bent. 2 bonded atoms and 2 lone pairs is also bent. And water is our poster child here. And these hydrogens, look how close these hydrogens are, because there's 2 lone pairs, okay? And we said lone pairs take up a lot of room. So these lone pairs are forcing these hydrogens closer together. 104.5. Again, don't worry about memorizing degrees. And lastly, last reminder that when you draw the molecule, you don't draw lone pairs. Okay, we just visualize atoms and bonds, but we consider the lone pairs when we name the geometry because lone pairs count as a charge cloud. Questions on that? Oh, I have a question in the chat. How can oxygen only have 1 bond? It doesn't have 1 bond. It has 2 bonds here, Abby. It's got a bond to hydrogen and a bond to another hydrogen. Did we say oxygen could have a bond? Or was there a particular slide? With sulfur? Was that on the table from earlier? Up here? Oh, I see what you're saying. She's looking at this molecule. We have 1 bond here. Well, here's what you find in chemistry. There's always exceptions to the rule. This molecule has something called resonance. Resonance are where bonds actually, what's the word I'm looking for? Bonds switch places between atoms. Okay, so remember, electrons are always moving. We like to think of bonds where electrons are sitting nicely between the atoms and they're still, and that's not the case. Okay, they're about as still as my 2-year-old is. Okay, so they're always moving. So the fact of the matter here is, at any given time, we may have a double bond between this oxygen and sulfur, and then that double bond may jump over to this sulfur and oxygen. Now, if you'll notice, this has 3 lone pairs. Okay, so all the electrons are there. It's just that, and this is not even actually a topic we're going to cover in our course, but it's that this molecule has resonance. So any one pair, this lone pair right here, will jump down here and make that second bond, and then the 2 electrons, let me erase. The 2 electrons right here will jump up on this atom, and they'll switch, okay? Electrons are always moving. And so it spends equal time having double bonds, both of those oxygen to the sulfur. It's just that there's resonance, and because of the number of atoms and the way things are, the sulfur doesn't like to carry the charge burden of having, it doesn't like to carry all of these bonds. Oops. That sulfur doesn't. That's a lot of electrons around the sulfur, plus it has its own lone pair. So that sulfur likes to keep things in a resonance, and so it'll push these oxygen, or these 2 electrons up on that oxygen, and then again it'll have resonance and things will switch the way I've drawn them. What I just said though to everyone, if you checked out for the past 3 minutes, check back in. That's kind of not a topic we'll get into in this course, but that is the explanation for why you saw 1 bond between that sulfur and oxygen. This is a review slide. So I'm actually going to move on because I think we've beaten this horse into the ground. Okay. Now, again, you can have an atom with more than one central, or a molecule, sorry. You can have a molecule with multiple centers, more than one central atom. So each atom that is a central atom, they don't all have to have the same geometry. They can have a unique geometry. Here's an example, okay? We have this molecule. The black spheres are our carbons, okay? So there's carbon 1 and there's carbon 2. This carbon right here on the left, this has right here, this is a tetrahedral. And then the carbon on the right is trigonal planar, okay? Because there's a double bond on it. So again, carbon is 90% of the time tetrahedral, but occasionally you can see it be trigonal planar when there's a double bond. Or carbon could also be linear. There's one molecule that I immediately think of where carbon is linear, and that is carbon dioxide. If you look at this, carbon only has 2 bonded atoms. And here carbon would be linear. But most of the time it's tetrahedral. Some of the time it's trigonal planar, depending on the number of double bonds attached to the carbon. Questions on that? Okay. So I put these rules here again for us to reference. It's all filled in. We're going to do some practice. So get some paper out, grab a pencil. First things first, rule number 1, you draw the Lewis structure, and then I want you to name the geometry for the central atoms. If you need to refer to that table several slides back, it's actually also in your textbook. If you're in chapter 4, I don't know what section it's in, but go to the section titled Molecular Geometry, and I guarantee you'll find, here's what table I'm talking about. This table right here. If you have your textbook with you, or the electronic copy even, I would try to find the page that I wish I would have written. It's table 4.2 if that helps. And so I would try to find that table, and it will help you with this. So let's go back down here, and let's draw this molecule. So I'm going to draw the Lewis structure for this. Remember, you first need to add up the total valence electrons. So I'm going to quickly do that. Carbon each has 4, so that's 4 times 3. We have so 26 valence electrons in this molecule. I commonly like to attach all my carbons. Whoops. Now I'm going to start putting hydrogens on my carbons. There's more than one way you can draw this. Remember, if you are drawing it differently than me, that's okay. I know my oxygen has to have 2 bonds, and it's got 2 lone pairs. And then I have space. I've got 5 hydrogens drawn in so far. I have space for 3 more. Where? Well, I have space for 2 on this carbon and 1 over here. So this is an appropriate structure. So now let's name the geometry of our central atoms. Any atom that has more than 1 bond is a central atom. So we have 4 here, 3 carbons and an oxygen. We're going to name the geometry for all of them. Well, it's very easy for these carbons. Every single carbon in our structure has all 4 single bonds. So 4 bonded atoms. I'm going to change to pink for a second. Let's zoom in. All these carbons, 4 single bonds. I'm going to just demonstrate with the first one. Okay, so we got 4 bonded atoms and 0 lone pairs. Anybody remember the geometry? Oh, page 118. Thank you, Kate, if you want to look at that table in the textbook, page 118. Anybody remember the geometry? There's 4 charge clouds here. 4 bonds, 4 bonded atoms, no lone pairs. We call that what? Tetrahedral, yes. And that's the case for all these carbons. So here's what I'm going to do. You can totally do this. It saves you a little bit of space. You don't have to write the word 3 times. All those carbons are tetrahedral. Okay, what about oxygen? We've got 2 bonds, 2 lone pairs. So total, that adds up to 4, I'm going to abbreviate, charge clouds. What do we call that? Anybody remember the geometry?
Linear.
Not linear, it's bent. It is bent, okay? 2 charge clouds is linear. But when we have 4 charge clouds and it's 2 bonded atoms, 2 lone pairs, this oxygen is bent. Okay, see how it's like a puzzle? You put all the pieces together to get the right name. Okay, let's look at the second molecule. And then you would want to go back through and make sure you've got all your electrons represented. I'm going to count in my head real quick. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I counted 26. Okay, carbon, we've got 2 of them. Each one has 4 valence electrons. Hydrogen, we've got 5 of them. Each one has 1 valence electron. Fluorine, we've got 1. That's got 7 valence. And oxygen, just 1, 6 valence. Again, I got 26. Okay. So let's draw our structure. I want you to go ahead and start trying to draw it. Remember, hydrogen and fluorine, they're going to have to be the perimeter atoms. Oxygens and carbons can be central atoms. Your structure may look different than mine. Make sure you put the lone pairs on. So that's what I drew. And I counted up 26 electrons on there between the bonds and the lone pairs. If you forgot how to count those, remember every bond is 2 electrons. So 2, 4, 6, and so on and so forth. So now we're going to name the central atoms. So carbon here and here, 4 single bonds, exactly what we saw earlier, tetrahedral. And oxygen, it looks the same as it does in the first structure, 2 bonds. Okay, so there's 2 bonds. And we've got 2 lone pairs. All right, total, that adds up to 4 charge clouds. So this one is bent as well. Any questions? Let's do NCl3. I think I have even more down here, but I'll probably let you practice those on your own time for the extra practice. So NCl3, total number of valence electrons first before we draw the Lewis structure. And if you're wondering how am I going about this, how am I getting all this correct, how am I Well, I've taught the class a few times, but I'm following these rules, right? So we're drawing the Lewis structure. Then we're adding up the charge clouds. And remember, these things are how we add up charge clouds. And then we're using that to predict the shape according to the table. All right, so that's how I'm going about these, step by step, boom, boom, boom. Okay, so total number of valence, nitrogen. We have 1 nitrogen atom. Each one has 5 valence electrons. Chlorine, we've got 3 of those. Each one has 7 valence electrons. 26 again. So I know chlorine is a halogen, and because it has 7 valence electrons, if you remember from covalent bonds, they share. We're trying to achieve an octet here. Here's a picture of chlorine. It's got that 1 unpaired electron, so it's just going to form 1 bond. So remember, halogens, they can only have 1 bond. So how do I know how to draw this molecule? Well, my chlorines are going to be on the perimeter. Nitrogen, it has 5 valence electrons. It wants 3 more. And the number of electrons that it needs to get 8. So if it has 5, 5 plus 3 equals 8. That matches the number of bonds it will form. So I know that this nitrogen is bonded to 3 chlorines. If you're lost on this, if you feel like I'm moving way too fast, if you can't keep up, you need to go back and watch the lecture from last Thursday, review our rules on Lewis structures. How do we draw these things? How do we know what's in the middle? How do we know what's on the outside? How do we know how many bonds an atom will have? Go back and rewatch that lecture. I know that sounds like more work, but you need to have a good foundation for Lewis structures to even begin to get molecular geometry correct, right? And then this nitrogen should have a lone pair. And if you count up all the electrons here, you should get 26. Okay, how do we name the geometry on this nitrogen? So we drew the Lewis structure. Now let's count charge clouds. So we've got 3 bonds, 3 bonded atoms, here, here, and here. So that is 3 bonded atoms, plus we've got a lone pair. Remember, all of these things are charge clouds. So that means we've got 4 charge clouds. So what do we name something that has 3 bonded atoms, 1 lone pair, and it adds up to 4 charge clouds? And if we go back and look at the, right here. 3 bonded atoms, 1 lone pair, we call that pyramidal. Whoops, I passed it. So this nitrogen right here is pyramidal. Okay, woo, question on how we did that. This should feel new. You're probably not super comfortable with it. I don't expect you to be comfortable with it right now. These things take practice. So I want you to attempt these other 3 on your own to give you some more practice with that. Email me or shoot me a screenshot of your work if you want to dialogue about it, getting the right answer on those. And that's it for geometry. Okay, so that's kind of a whole unit in and of itself from chapter 4. We'll definitely have this on the exam. We're moving on now. Let's have a new topic. So we're not going to finish the lecture today. We've got a lot of slides left. And in fact, we won't even get to the poll questions that I had because they're all on this stuff moving forward. So what I'm going to do, anything we don't finish today, I will make a pre-recorded video and I will post that on Blackboard. So we'll talk about polar bonds for a second, but electronegativity, polar molecules, and naming binary compounds. If you look at the slides we have to come, I'll do videos, probably individual videos, like short 5 to 10 minute videos. And post those on Blackboard so you can catch up on this material. We're still responsible for getting this done. So that'll be posted. And then I think I forgot to announce this at the beginning of class. If you read my email, I'm unavailable Thursday. And we will have, that's the one day, I hate to do it, but it'll be the one day we'll have recorded lecture video. Okay, so I'm not going to do one big hour-long video. I'm going to break it up into segments, and I'll number them. Video number 1, 2, 3. So we're starting chapter 5, which is chemical reactions, on Thursday. And I will cover probably the first half of that PowerPoint. And I'll post those videos Thursday morning to Blackboard. So we will not meet live on Thursday. You can watch those in your own leisure time on Thursday. All right, let's talk about polar bonds before we wrap up, because we've only got a few minutes left. Polar bonds. So covalent molecules, remember, we're not talking ionic molecules here. Covalent molecules are different. We're sharing electrons. Sometimes things are shared evenly and sometimes they're not. So I want you to look at the molecules on this slide. And then I want to read this question. What is the difference between the two molecules up top and the molecule on the left? Can anybody tell me? Just the obvious difference here. Don't tell me one's rainbow and the other are not rainbow. Look at the atoms. What do you notice?
The ones up top are the same, and the ones down low are different.
Yes. So up here, the two molecules on top, they're both two identical atoms bonded together. All right. That's the similarity between these two molecules. Down below, we have two different atoms bonded together, okay? This one is two different atoms. Now, let's talk about the molecules up top for a second. When you have two identical atoms bonded together, here's what I know. The nucleus in each of those atoms is the same, right? Because it's the same element. Here's what else that means. It's the same number of protons in each nucleus, okay? So we have the same nucleus on each side of the bond, which means the same number of protons. Okay, so I'm going to use a tug-of-war analogy to explain polar bonds versus non-polar bonds. So if we have the same number of protons, I want you to imagine that these electrons, which are being shared, they're being pulled towards the nucleus. Remember, there's attractive forces at play. These electrons, they're being pulled towards this nucleus, and there's one proton here, and then there's one proton here as well. And they're also being pulled towards the nucleus on the right. So those electrons are being pulled. Now, here's what we can say about the tug-of-war match. If this is a tug-of-war match, which side is going to win? Well, we don't know, right? Because it's their equal strength. The team on the left and the team on the right, equal strength. So the electrons are shared equally. They're being pulled equally in those opposite directions. And the same thing with chlorine. Chlorine has 17. Sorry, I'm back to pink. I forgot. Chlorine has 17 protons, and that's on both sides here. So when we consider the tug-of-war match, it's the same concept here. These electrons in the middle, they're being pulled equally in opposite directions. This is a non-polar bond. When electrons are shared, keyword, equally, it's a non-polar bond. So what is a polar bond? It's when electrons are not shared equally. So a polar bond, we have two different atoms, okay? And here, the electrons are not shared equally, okay? How do we know this? Well, we have 17 protons on the right in that chlorine atom, and we have only one proton in that hydrogen atom. So the electrons, the two electrons in this bond, which side are they going to be pulled towards the most? Are they going to be pulled towards chlorine or towards hydrogen? They're going to be pulled towards the side with more protons, with more positive charge. So they're going to be pulled towards chlorine, all right? Now, when this happens, we call this a polar bond because the electrons are shared unequally. That is a polar bond. Any bond where the electrons are shared unequally for now, we'll call that a polar bond. We're actually going to put numbers to this and see how unequally things are shared in a little bit. But last thing we'll talk about before we go today are these signs right here. So when you have a polar bond, you assign one atom in the bond as electron rich, and you assign the other atom in the bond as electron poor. The atom that is pulling the electrons with a stronger pull because they've got more protons in the nucleus, that is the atom that's going to be electron rich. Okay, so this is electron rich. We say it is partial negative. Why are we putting this? And that's what this little delta with a minus sign, okay? This red sign right here, delta minus, it's a lowercase Greek delta. The squiggle with a minus, we call this a partial or a semi-negative. We're not talking about ions, anions and cations here. That is when electrons are fully traded. But it's just that the electrons are closer to the chlorine, which gives it more of a negative charge. Okay, so we say it's partially negative. The hydrogen is electron poor. All right, or if you're from Louisiana, you say electron po. And so we say this is partial positive. So a little delta with a plus sign, you assign the atom that is, well, it's not pulling the electrons toward it as strongly. You assign that with a partial positive, you assign the atom that has more protons in its nucleus, and therefore it's pulling electrons towards it with a partial negative. So, all right, that's how we define polar bonds, and we'll get into the rest of the content. I'll post videos by tomorrow at some point, so you can watch those. And then Thursday, I'll post our other lecture material. If you have any questions, I will stick around. And other than that, thank you for joining us today. Question on the chat: will it always be represented as the partial positive negative? For polar bonds, yes, we'll use those signs very frequently, Susanna. Those are always. Can we access